You've probably heard about black holes, those mysterious cosmic vacuum cleaners that suck up everything, even light. But here's a cosmic plot twist: black holes aren't actually holes. That's right. Despite the name, a black hole is not a hole at all. It's an object, an incredibly dense, compact mass packed into a tiny space, so powerful that nothing can escape its gravity. Think of it as the universe's ultimate heavyweight champion, but without a boxing ring. Imagine if you tried to create a hole by digging into the ground, but instead of an empty pit, you ended up with a giant invisible sphere so dense it warps space and time around it. That's a black hole for you. No hole in sight. And before you ask, no, you can't fall into one and come out the other side. Sorry, no cosmic shortcuts or wormhole Uber rides here. Next, we'll dive into what makes a black hole so dense, and how it bends space and time in ways that seem stranger than science fiction. So what exactly makes a black hole so dense? Imagine squeezing the entire mass of our sun, yes, that giant fiery ball, into a sphere just about 12 kilometers across. That's roughly the size of a small city, but packed tighter than your jeans after Thanksgiving dinner. This insanely dense object creates a gravitational field so strong that nothing, not even light, can escape once it gets too close. That boundary is called the event horizon, which sounds fancy, but really just means the point of no return. Cross that invisible line and you're stuck. No calls home, no Instagram updates, just eternal cosmic silence. Kind of like forgetting your phone charger at home, but way worse. Inside the event horizon, gravity pulls so hard that it warps space and time themselves, bending the rules of physics like a cosmic yoga master. And no, this doesn't mean you'll turn into a stretchy spaghetti noodle if you fall in, although physicists have a fun term for that: spaghettification. Basically, you'd be stretched out lengthwise like cosmic pasta before you get squished flat. So if you were hungry before, this might be the ultimate reason to avoid black holes. Black holes are born when massive stars, much bigger than our sun, run out of fuel and collapse under their own weight. Imagine a star that's been burning bright for millions of years, suddenly losing its balance and collapsing like a house of cards. But instead of just falling over, it compresses into an insanely dense point called a singularity, where all the star's mass gets packed into zero volume. Talk about being compact. This dramatic collapse creates the black hole's event horizon, sealing off the singularity from the rest of the universe. It's like the star's dramatic mic drop moment, no encore, just silence. Black holes come in different sizes, from stellar black holes formed by collapsing stars, to supermassive black holes lurking at the centers of galaxies, including our very own Milky Way. These cosmic giants can be billions of times heavier than the sun. Basically, the ultimate heavyweight champions of the universe. And don't worry, the odds of one sneaking up on Earth are astronomically low, probably less likely than your coffee going cold before your first sip. Near a black hole, gravity becomes so intense that it warps not just space, but also time itself, a concept known as gravitational time dilation. This means that time moves slower the closer you get to the black hole compared to someone far away. Light traveling near a black hole is bent dramatically by its gravity, a phenomenon called gravitational lensing. This bending can magnify and distort the images of stars and galaxies behind the black hole, allowing astronomers to observe objects otherwise hidden from view. At the event horizon, the escape velocity equals the speed of light, so even photons cannot escape. This makes the black hole appear completely dark, hence the name black hole. Understanding how light and time behave near black holes helps physicists test Einstein's theory of general relativity under extreme conditions, deepening our understanding of the universe's fundamental laws. Next, we'll explore the mysterious singularity at the heart of a black hole and what it means for physics. At the center of a black hole lies the singularity, a point where density becomes infinite and the known laws of physics break down. It's a place where space and time as we understand them cease to exist, and gravity's pull is unimaginably strong. This singularity challenges physicists because current theories, general relativity and quantum mechanics, offer conflicting descriptions at this extreme scale. Resolving this contradiction is one of the greatest quests in modern physics. Some theories suggest that new physics, possibly quantum gravity, will replace our current understanding and explain what really happens inside a singularity. Until then, the singularity remains a profound mystery, a cosmic enigma at the heart of black holes. The existence of singularities implies that our universe may have boundaries in understanding, pushing scientists to explore beyond classical physics, to uncover the fundamental nature of reality. Black holes aren't just cosmic sinkholes, they can also be powerful engines driving some of the most energetic phenomena in the universe. Around many black holes lies an accretion disk, a swirling superheated disk of gas and dust spiraling inward. As matter accelerates and heats up, it emits intense radiation, including X-rays, which astronomers can detect across vast distances. Some black holes produce relativistic jets, narrow beams of particles accelerated close to the speed of light, shooting out from the poles of the black hole. These jets can extend thousands of light years and influence the evolution of entire galaxies by regulating star formation. These energetic processes reveal that black holes play a crucial role in shaping cosmic structures, far beyond their reputation as mere gravitational traps. Despite their name, black holes can slowly lose mass over time through a process called Hawking radiation, predicted by physicist Stephen Hawking. This radiation arises from quantum effects near the event horizon, where particle-antiparticle pairs spontaneously form. Occasionally, one particle escapes while the other falls into the black hole, resulting in a gradual loss of energy and mass. For most black holes, this evaporation is incredibly slow, far longer than the current age of the universe. However, for very small black holes, Hawking radiation could cause them to evaporate completely. This surprising insight connects quantum mechanics, thermodynamics, and gravity, offering a glimpse into a possible theory of quantum gravity. Black holes have captivated human imagination for decades, inspiring countless works of science fiction, movies, and art. From the wormholes and time travel fantasies to mysterious disappearances and alternate universes, black holes fuel our curiosity about the unknown. While many ideas remain speculative, they encourage scientific inquiry and push the boundaries of our understanding. Studying black holes bridges the gap between the cosmic and the quantum, reminding us of the universe's profound mysteries waiting to be unraveled. Detecting black holes is a complex challenge since they emit no light themselves. Instead, astronomers rely on indirect evidence. Observations of stars orbiting invisible massive objects, X-ray emissions from accretion disks, and gravitational waves from black hole mergers provide compelling proof. The groundbreaking detection of gravitational waves in 2015 confirmed that black holes can collide, merging into even larger black holes and releasing tremendous energy in the process. These discoveries have opened a new era of astronomy, allowing us to listen to cosmic events and explore black holes in unprecedented detail. Black holes aren't holes, but some of the most fascinating objects in the universe, regions of extreme density, gravity, and warped space-time. Their study challenges and expands our understanding of physics, from the very large scale of galaxies to the smallest quantum effects. Black holes serve as natural laboratories for testing the laws of nature under extreme conditions, offering clues to the deepest questions about space, time, and reality itself. As science advances, black holes will continue to illuminate the frontiers of knowledge, reminding us that the universe is far stranger and more amazing than we can imagine.